So the first one, negative x to the negative 2, that one we should just be able to apply the power rule to. So we'll go up to a power of -1, and then we'll divide by -1, and we won't forget our plus c. So this becomes just a 1 over x plus a constant. Is that what everybody got for that one?
Yeah.
Cool. All right, what about the next one? The 3x to the 4th is again just power rule, so that should be 3/5 x to the 5th. And then the minus 2x to the -3, that'll be a -2, and we'll go up to x to the -2 and divide by -2. So that one just becomes what? Just x to the -2, or 1 over x squared. And then what about secant squared x?
Just goes tangent x.
Should just become tangent x, right? And plus a constant. Everybody good there?
Yes.
Okay. What about this one? This one is just straight off that rule sheet. What is that one?
Inverse tangent u plus c.
Yep, inverse tangent of u plus a constant. And what about 2e to the x down there at the bottom?
That's just 2e to the x, right?
It's just 2e to the x, right? The derivative of e to the x is e to the x. The integral of e to the x is e to the x. And put a constant in front of it, that doesn't change anything. So the integral of 2 to the x is 2 to the x. What about the integral of secant x tangent x?
Secant x.
Should just be secant x. And what about the integral of this one? This is x to the 1/2, right? So that should become x to the 3/2, and then we'll divide by 3/2, or it should become a minus 2/3 x to the 3/2. Everybody feel good about those four?
Yeah.
Any issues, any questions? All right, let's do a definite integral. So first off, what is the integral of x cubed plus 1?
It's an x to the 4th divided by 4.
So the 4th divided by 4, and then the plus 1 is?
It's just 0. Or wait, sorry, I have like a brain fart.
Anybody out there? What's the integral of 1?
X.
Yep, should just be x, right? Any constant just gets the x or whatever the variable is attached to it. And when we were doing the indefinite integrals, we added a plus c to it. We don't need that for the definite integrals. I'm going to write it here, but we don't need it for a definite integral. And I'll show you why right now. So what do we need to do with this according to the second part of the fundamental theorem of calculus? We need to evaluate it at 3 and evaluate it at -1 and find the difference. And so this is how we write that. We write evaluated from -1 to 3. Sometimes you might see me write it with a vertical bar, right? Like we did with the derivatives. But I'm just going to do this from -1 to 3. And so then we'll plug in 3 and plug in -1 and subtract. So what happens? Plug in the 3, right? 3 to the 4th over 4. What's 3 to the 4th? That's 81. So 81/4 plus 3 plus some constant minus -1 to the 4th over 4 minus 1 plus some constant. Well, what happens to the two constants?
They add up to 0.
Yeah, they're going to just cancel each other out, right? The plus c and the minus c are going to cancel each other out. This c we're not ever going to need when we do a definite integral. It'll just cancel out every time. So you can ignore the plus c and not put that in for any definite integral. And so then what do we get? We got 81/4 minus 1/4, which is 20, plus 3, and then plus 1. So we end up with a value of 24 for this integral. Good or no? And that was a lot easier than doing the limit as n approached infinity of the sum from k equals 1 to n of x sub k cubed plus 1 times delta x, with delta x equal to 4 over n and x sub k equal to negative 1 plus 4k over n. I think this was a lot easier. What do you think?
Yeah, it's a lot easier.
Agree.
Yeah, much easier. All right. What about this one? What should we do first?
Expand the r plus 1 squared.
All right, so let's integrate from negative 1 to 1, r squared plus 2r plus 1 dr. All right, so I want you guys to try to do the rest of this one on your own. So I'll give you like 2 minutes to integrate and evaluate that. You guys think you could do that?
Yes.
All right, ready, go. So our integral was hopefully r cubed over 3 plus r squared plus r. Everybody agree with that?
Yes.
All right, and we'll evaluate from negative 1 to 1, which would give us 1/3 plus 1 plus 1 minus negative 1/3 plus 1 minus 1. And that's 7/3 plus 1/3 is 8/3, and then plus 1 minus 1 will stay as 8/3. Good or no?
Good.
All right. So what I'd like you to do right now, really quickly, before we move on to the next slide here, is take a look at the homework that is due on Monday night. And look at number 1 and then A through J. So everything from 1A through J or 2A through F, I think you should already be able to do. So I'd like you to take a look for just a second at those and see if there are any in there that you think you're not sure what to do with. I'm not going to do them, but I'll talk about like the process and maybe do one that's similar to it before we move on to the next topic.
For 1D, I was just like doing it last period, and I got the integral of tangent x, and I noticed that wasn't on the sheet. I don't know if I just did my algebra incorrectly here.
You did your trig incorrectly. Yes.
Okay,
So,
that makes sense.
I'll start that out, or actually, we can just do that one. It's the integral of what? Sine x over 1 minus sine squared x, right?
Yeah.
Dx. So that should be the integral of sine x over cosine squared x if you were to rewrite that.
Oh, I just put cosine x. Oh, that's fine.
That's why. So
All
yeah,
right.
cosine squared x. And so then that gives you a tangent x times a secant x, which is an integral you should know. Becomes that, which you can integrate. Anybody else? Any other ones on there that you might not be totally sure about? 1A through J or 2A through F?
Like, wait, by the end of today, are we going to be able to do more than that? Or is that like after today, that's all we're going to be able to do?
No, 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 no. By the end of today, my hope is that you'll be able to do almost all of this sheet.
Oh, okay.
You'll definitely be able to do all of number 1 and at least through H of number 2. And a couple of the other ones. You'll probably be able to do everything but 2I and 2. Yeah, probably everything but 2I, 2L, and 1Z. Maybe 1W, V. Yeah, 1V, 1W, 1Z. A few of them you won't be able to do still, but most of them you will. All right, so you guys all feel like you're good with the ones I've been saying though, 1A through J and 2A through F? All right, cool. In that case, we will just continue moving forward. So what we're going to do is we're going to look at how changing some variables around can affect your antiderivatives or your integrals. And specifically, how the constant of integral, this is sometimes called our integration constant here, the dy, sorry, the dx or the du, how integrating in terms of a different variable might affect things. So we're going to do an integral of f of x dx. We're going to do an integral of f of u du, given these two functions up here. And we're going to do an integral of f of u dx. And we should see that each of these three things will come out to be completely different just based on the variables that I put in here with these small little substitutions that we might make with u equal to x squared. And the most important thing that we'll notice is that these two, f of u and f of u, which are the same function, will give us different answers depending on if we integrate it in terms of u or we integrate it in terms of x. And so one important thing that we need to note always about integrals is that if we're going to integrate it, the variable inside the function has to match up with the variable of the dx or the du. So this one, f of x dx, I should just be able to integrate straight up the way it is. F of u du, I should be able to integrate. As soon as I write f in terms of u and then I have a du, I should be able to integrate. But this one, where I write f in terms of u and it has a dx, we're going to have to do some extra stuff in it to be able to allow us to integrate it. So very important that those have to match up. You can't integrate something that is in terms of u in terms of x. Just like, we can't, without using our implicit differentiation method, we couldn't differentiate a y in terms of x, right? Without using the chain rule, which got us around that. Well, effectively, what we're going to be doing for the rest of the day today is we're going to be doing the chain rule in reverse with integrals. And we call them U-Substitution Integrals. But for now, we're going to start with this. So first off, what's the integral of f of x dx? F of x is x cubed plus 1, right? What's the integral? Should be pretty straightforward. Should be what? I think we just did this one a minute ago. Except it was in
X to the fourth over 4 plus x.
X to the fourth over 4 plus x, right? Plus a constant. Great. Easy enough. All right. What about this one? We're going to do it in terms of u, and we need to write f in terms of u. Now, I don't necessarily need to look at this yet. What is f of u? How would I write f of u?
Would it just be u cubed plus 1?
Yep, it would just be u cubed plus 1. Exactly. And now we integrate that. What do we get? U to the fourth over 4 plus u plus a constant, right? But what did it say we wanted to do? We wanted to put them all in terms of x in the end. So what does that actually become if I put that in terms of x?
X x to the 8th over 4 plus x squared plus c.
And we'll note that the variables here made a difference because u equaled x squared caused a change here. But for this one, when it's f of u, right, u cubed plus 1 dx, we're still integrating u cubed plus 1, but we have to do it now in terms of x. And so in order to integrate this, I can't have a u inside of here. So I have to change that into terms of x's now. And so what would u cubed plus 1 be in terms of x?
X to the 6 plus 1.
That would be x to the 6 plus 1 dx, which should integrate to become x to the 7th over 7 plus x plus a constant. And so we'll note here that even though for both of these last two, we were integrating f of u, we got very different answers because for one, we did it in terms of u, and for the other, we did it in terms of x. And so it's very important that when we're doing these u substitutions, we make sure that all of our variables in our function line up with our dx or our du or our dz or whatever variable we might have. Good? We see that if we don't, we're going to get different answers than what we should get. Hopefully we see that. All right. So let's take a look at something like sine x times e to the cosine x. And if you were to take out your integral rule sheet and look at it, you would see that there is no rule for this integral. So we're going to have to make some sort of a substitution and turn something into terms of u. And what we will most of the time do for a U-substitution integral is you will substitute out the part of the more complicated piece of it. So there's two pieces to this. There's sine x, which is being multiplied by e to the cosine x. So what's more complicated, sine x or e to the power of cosine x?
E to the power of cosine.
Yeah. And so what we want to do is we want to substitute out the part of e to the cosine x that makes it complicated. And the part that makes that complicated is the cosine x, right? Because e to the u is just a simple function to integrate. And if I just had this, the integral of e to the u du, life would be really easy, right? What would that integral be?
E to the u.
Just be e to the u. So if we could turn the e to the cosine x into e to the u, then we'd be off to a good start, because the hardest part of this to integrate is now easy to integrate. The issue is that we still have a sine x attached to the front of it, and we have a dx and not a du. So we're going to have to find a way to turn that dx into a du. So my next question is going to be, how will I figure out what du is? How do I get a du into there? And I want to have a du in there, don't I? Because if I had a du in there, then I'd be getting closer to being able to integrate things in terms of u, which is what we want to do for these u substitution integrals. So what's du? Okay, let me try this a different way. I'm going to ask you the exact same question I just asked you. What's du?
Negative sine x?
Wonderful. Isn't du just negative sine x dx? Isn't that how we find du using a differential back from our derivatives units? We're taking the derivative of both sides. On this side, we're doing it with terms of u, so du. This time it's in terms of x, so it's got a dx attached to it. So du equals negative sine x dx. Good or no? Everybody good with that or not good with that? Okay. So if we had negative sine x dx over here, I could replace it with a du, but I don't quite have that, do I? If I could replace a negative sine x dx with a du, I'd have a du over here, right? True? How can I get a negative sine x dx over here?
Wait, sorry, can you repeat that?
Okay. We want to be able to integrate this in terms of u, which means we need to have a du over here. We know that du equals this. So if I had this, I could replace it with a du. Do I have this over here within my integral?
No, right. Could you do like du times e to the u?
Sorry, du times what?
Times e to the u?
I mean, that's effectively what I'm going to want to have. I'm going to want to have an e to the u times a du. That's what I want to have, right? I mean, I want to have a du over here, but I want to be able to get rid of all the junk with the x's in it. So
Could you put that du equals negative sine x dx in terms of dx, so you can plug it in and then cancel out the sine x and negative sine x, because that'll be in the denominator.
okay, yes, so that's one way that we could do this. We could say dx equals du over negative sine x, and then I would replace the dx with that. I was hoping to see that, you know, we almost have sine x dx over here already, though, don't we?
Yeah.
So if I could just attach a negative sign to this, I could replace the negative sine x dx with the du. Okay, so I'm going to do this two different ways here. First way is what somebody was just saying, right? Is we had sine x e to the u dx. Well, dx is equal to du divided by negative sine x. And so what would that give us?
Negative e to the u du.
Negative e to the u du. And what is the integral of negative e to the u du? It should be negative e to the u plus a constant, or negative e to the cosine x plus a constant. This right here is not necessarily my preferred way to do it. If you prefer to solve for dx and plug it in like this and solve it out, that's fine. What I like to do is I just like to build this negative sine x dx into here. So I just put a negative sign here. And if I put a negative, if I multiply all of this by -1, I gotta multiply it by -1 a second time. So I just put another negative sign and say this is negative an integral of e to the u, and then the negative sine x dx gets replaced with the du. And you end up with negative e to the u plus a constant, or negative e to the cosine x plus a constant. Either way, it comes out to be exactly the same. So if you prefer to solve for dx and plug it in and simplify, that's fine. Or if you prefer to build the dx into it and then just cancel it out, that's fine too. Generally, this is how I will demonstrate the problems because that's the way I like to do it. Does that make sense to everybody or no?
Makes
Could
sense.
you maybe like go over the process when you added the negatives again?
Yep. I said I needed to have a negative sine x dx in there. So I put one in. I can multiply by -1 as long as I multiply by another -1 to cancel it out, right?
Oh, okay. I see.
So I multiply by -1 and I multiply by -1. This -1 disappeared with the negative sine x dx to become the du, and this negative sign stayed. Good or no?
Yeah, that makes sense.
Okay. Cool. Any issues, any problems? Everybody okay there? Okay, let's do another one. Any thoughts on what I might want to substitute out of this?
Everything under the radical.
Okay. So we'll let u equal 5 plus 2x cubed. And that's a good choice because the more complicated piece of this is the root 5 plus 2x cubed, and the part of it that makes it complicated is the 5 plus 2x cubed. What is du going to be?
X.
6x squared dx.
6x squared dx. And do I have a 6x squared dx within my integral already? To cancel out to become a du.
No.
No, but I have the x squared and I have the dx, right? So all I would need to do would be to multiply this thing by 6. Right, if I multiply it by 6, now I have the 6x squared dx, don't I? But if I multiply it by 6, how do I have to cancel that out? I also have to multiply it by
1/6.
1/6. So I'll just put a 1/6 on the outside. 1/6 times 6 cancels, but the 6 will stay with that x squared dx to become du. And we'll have 1/6 the integral of root u du. Good or no?
Good.
Okay. Now we integrate. This becomes 1/6. And our integral of square root of u, that's u to the 1/2, so that'll go up to u to the 3/2. And we'll divide by 3/2 or multiply by 2/3 plus a constant. And that's going to give us 1/9 of 5 plus 2x cubed to the 3/2 plus a constant. And I know that 1/6, right, gets distributed to the constant, but 1/6 of a constant is a constant, isn't it? So traditionally, we'll just normally put a plus c there at the end when we're done. Good or no? Any questions there? Any issues with that?
So is the bracket just a way to indicate like an integral, or do you just use that as like multiplication?
Yeah, it's just like a parenthesis. It's just brackets, parentheses, the same thing. I mean, I've already finished the integral by the time I get to there, right? I've integrated that. That's what I got.
Yeah.
I just,
Um,
I don't know why I put brackets instead of parentheses, but they're interchangeable.
when you integrated du, why did it become a constant? Or am I looking at it wrong? Like what happened to du when you integrated it?
Whenever you integrate the du or the dx or whatever it happens to be there, it goes away. And because the summation is telling you, and that's what this integral is, it's a summation. It's the limit and the summation together. It's saying add together this thing times this thing for whatever interval we've got. Right? And so the dx part of it is the widths of the rectangles, and this is the heights of the rectangles. They're being multiplied together to get the areas. So we're summing together all of the areas. So the integral of all of this dx just becomes whatever the integral of that function itself is.
Oh, okay. Thank you.
Yep. Does that make sense? Yeah.
Yeah.
Okay. All right. Any other questions on that one? All right. Okay. I want to skip that one for a second. Let's just do this. Let's integrate cotangent x dx. So first thing you'll probably do is you'll look at your rules sheet and see if there's a rule for cotangent x, and you will discover that on that paper I gave you there is not a rule for it, correct?
Correct.
Okay, so let's rewrite this. The only way that seems reasonable to rewrite cotangent, I mean, we could do 1 over tangent, but that's probably not going to do anything. So let's rewrite this as an integral of cosine x over sine x dx. And then let's see if we can do a U-substitution with it. So what would our substitution be? Any thoughts?
Could you just substitute that entire fraction?
So let's think about that. If we try to substitute out the entire fraction, let u equal cosine x over sine x, or let u equal cotangent x, right? Then du would be what? What's the derivative of cotangent? Would be negative cosecant squared x dx. It's going to be very hard to build in a negative cosecant squared x into that. Would you agree?
Yeah.
Yeah. So we're not going to be able to do that. We got to just substitute out one piece of it. If it was just like not a fraction, right? If it was not a fraction, then make it easier. So maybe the part of that that's making it more difficult is the fact that there's a fraction there.
Oh, could you use u equals 1 over sine x, or like cosecant x?
Okay, so if I let u equal 1 over, it's not 1 minus 1 over sine x, then that's going to, if I rewrite this, 1 over sine x would be now u, we'd have u cosine x dx. And what would du be? It would be the derivative of 1 over sine, or the derivative of cosecant, which would be negative cosecant x cotangent x, which is going to be an issue, I think. Yeah?
Yeah.
Yeah. So good idea, but not quite going to work out. Other thoughts on that?
What if it was just the sine of x?
All right, what if we just did u equals sine x? Well, let's take a look. What would du be then? At least that one's got a nice derivative to it, right?
Cosine x.
Yeah, so du should just be cosine x dx. And if we were to replace that in here now, cosine x dx is in the numerator, right? So that'd be a du over u. Is that one that we know how to integrate?
ln u plus c.
Yep, this should integrate to become natural log, and it's not just u, it's natural log of the absolute value of u plus c. And we'll talk about why that's absolute value just in a second when we finish this problem up. But let's resubstitute the u back in, natural log absolute value sine x plus a constant. And so this, this integral of cotangent x to be natural log absolute value sine x plus a constant shows up pretty often enough that it might be helpful to you to just have that one memorized. And so then the next question then, before we go to the next problem, is how come when we integrate 1 over x, let's say, I'll just make a new page for this, right? Why is the integral of 1 over x dx natural log absolute value of x? Well, right, when we took the derivative of natural log of x, you just get 1 over x, right? So the integral of 1 over x should be natural log of x. It seems like. True? Doesn't seem any reason to put an absolute value on it, but there is. And the reason we put the absolute value on it is because what's the domain of 1 over x?
Everything but 0, right?
Should be what?
Just everything but 0.
Yep, everything but 0. Negative infinity to 0, 0 to infinity. Right, but what about the domain of the natural log of x without an absolute value on it? That's just 0 to infinity, right? And so in order to make sure that our integral has the same domain as our original function, we throw it in to an absolute value, right? The domain of this natural log of absolute value of x is 0 to infinity, is negative infinity to 0 union 0 to infinity, right? Because we can plug negative values into that if there's an absolute value on it. Good or no?
Yeah, that makes sense.
All right, cool. Let's do another one, very similar. Let's see if we can find, and maybe you guys can try this one on your own. In fact, I think that's a good idea. See if you can come up with an integral for tangent x dx using a U substitution. I'll give you guys like 2 minutes to see if you can do that on your own. Sound good?
Yeah.
Ready, go. So what'd you do? You wrote it as hopefully an integral of
X over cosine.
sine x over cosine x dx. And what was your U substitution?
U equals cosine x.
All right, U equals cosine x, which makes du what?
Negative sine x dx.
Negative sine x dx. And if we go back in here, the bottom is going to become a u, but we need to put a negative sign inside to get the negative sine x, which means we'll put a negative sign outside, and we'll have negative du over u, or negative natural log absolute value u plus a constant. Good or no?
Good.
Cool. Sometimes you might see this written also as natural log absolute value secant x plus a constant. That's just using the log rule to take this coefficient of -1 and cosine to the -1, not the inverse cosine, but cosine to the -1 power is 1 over cosine, which is secant. So it's natural log absolute value secant x plus a constant. So these might be good ones also to just to note for tangent x. All right, let's do this one now. The integral of cotangent 7x dx. Since we now know what the integral of cotangent is, what could we do for a substitution here?
Just let u equal 7x.
Okay, so if u is 7x, then du will be 7 dx. And we'll end up with what? An integral of cotangent u and a dx, and so we'll have to throw in a 7 and a 1/7. That makes sense to everyone? And we get 1/7 the integral of cotangent u du, or 1/7 natural log absolute value sine u plus our constant, or 1/7 natural log absolute value sine 7x plus the constant. Good or no? Any questions, any issues with any of these? All right, we're going to stop there for today.